Welcome back. So in example 4, we're looking at Simpson's rule. We're still going to go back and look at using the function from example 2, which is actually the same function that we've been using this whole time, which is 1 over x. And so when we need, for the Simpson's rule error bound, we need the fourth derivative of that function. We can use the fact that we've already taken the first derivative, the second derivative, when we were trying to get the error approximation using the trapezoidal rule. So let's just continue taking now the third derivative and then the fourth derivative. And when you do that, you get that the third derivative, is negative 6 over x to the fourth. And then the fourth derivative, which starts using the number in parentheses, that's going to be 24 over x to the fifth. Third derivative, you still put the 3 tick marks, but then the fourth derivative, you just start writing numbers because it gets really tiresome to write all those little primes. I just realized Amazon Prime. Nice. Gotta fit that joke in there somewhere. Okay, I'm gonna go back and change my Math 180 videos and put that in there somewhere. Okay, so here the absolute value, at least on the interval from x equals 1 to x equals 2, is going to be the absolute value of the fourth derivative will still just be 24 over x to the fifth, because our x values are going to be from 1 to 2 there, and everything's still positive on that interval. So the absolute value bars don't really do anything. So what we'll do is we'll draw a quick sketch of 24 over x to the fifth, which, again, the main thing is that we just need to know that it falls as you go to the right. It's a decreasing function. So when we look over our interval from 1 to 2 and look to see where is the biggest possible value for the absolute value of the fourth derivative, well, it's going to be over here on the left side. Now, if this were an increasing function, that would be different. If it were an increasing function, if it went up as you go to the right, well then you would have your biggest function value over here to the right. So you'd plug in x equals 2 to figure out the biggest value for the absolute value of the fourth derivative. But that's not happening here. We have our function is decreasing, so it's going to appear, the maximum will appear over on the left side. So let's plug in then x equals 1 into the absolute value of the fourth derivative. And we get 24. So that's our m. It's our upper bound on the absolute value of the fourth derivative on our subinterval, or on our interval. So we can feed that into the error bound formula for Simpson's rule, which is m times b minus a to the fifth, that's 2 minus 1 to the fifth, over 180, kind of a nice number, you know, half of 360. And then we have n to the fourth. Remember the n here from example 2 was 4. So feeding all this in, we get 1 over 1,920, which is a much smaller fraction than 1 over 96. So the Simpson's rule here is doing a lot better with 4 approximating units, or with 4 subintervals. 4 subintervals. So remember, 4 subintervals means actually 2 approximating units, 2 parabolas. So then here, when we write this as a decimal, we have 0.0005283 repeating. And this is going to be correct to at least, well, we have here there's a 0, here there's a 0. The thousandths place is also a 0, but unfortunately the place value after that is a 5, which could, if you're doing plus or minus, it could swing this this thousandth place to a different number. And so this is going to be correct at least to 2 decimal places. That third one we're a little bit uncertain about, because that 5 could then swing that thousandth thousandths place value. Thousandths is a very hard word to say with your tongue. Okay, just to give a little numerical example of that. Here, let's say that your approximate area was 1.234. If you took that and you were looking at plus or minus the error, let's do minus the error, you would end up with 1.23348, and this would then change that thousandths place from a 4 to a 3. Even if you rounded it to the nearest thousandths, it would still change that place value there. So unfortunately, that happens when you have like a 5 or bigger in the next place value. If this were a 4, then that kind of thing wouldn't happen. So anyway, this is just off to the side as an example of why we can only be safe out to 2 decimal places. That's it for example 4. In the next video, we'll tackle example 5. Thanks for watching.